Modern infrastructure is under constant, invisible assault. Gravity, wind, electricity, and data are relentless forces pushing against the physical and digital structures we rely on every day. If any single element is forced to bear the full brunt of that stress, it inevitably reaches a snapping point, triggering a catastrophic collapse. To prevent those single points of failure, engineers don't try to build immovable, indestructible objects. Instead, they rely on a universal principle called load distribution, a way to intelligently scatter intense stress across a wider network. We can see this principle actively at work across three different domains: spatial distribution in physical architecture, temporal distribution in the electrical grid, and algorithmic distribution in digital networks. The goal is to design a cooperative system where multiple components flawlessly share the burden, ensuring no single piece ever has to hold the world up on its own. Take a high-rise building. Beyond the sheer weight of its own concrete and steel, it has to account for what civil engineers call a live load, the changing, temporary weight of moving people, heavy furniture, or even a sudden accumulation of snow on the roof. To manage that weight, engineers calculate tributary areas. This is a specific, mathematically defined zone that a single structural member, like a central column, is responsible for supporting. If a heavy object sits inside that area, its weight is assigned to that column. But the column doesn't just absorb the weight, it acts as a conduit. Through what is known as a load path, the structure actively shatters a concentrated live load into smaller force vectors. Those vectors are routed horizontally through beams and trusses, then vertically down the column, and finally dispersed deep into the foundation below. By forcing the weight to travel through this path, static load balancing takes a highly localized, potentially destructive pressure and disperses it safely across the building's entire footprint. While civil engineers distribute weight across physical space, the electrical grid distributes its burden across time. This chart shows electricity demand at a substation over a 24-hour period. Looking at the thick total line on the graph, you can see a sharp rise in the early evening. This is peak demand, the moment when millions of people return home, turn on lights, and run appliances simultaneously. Notice how close that total line gets to the dashed horizontal line at the top, representing the safe capacity threshold. If demand crosses that line, the grid fails. This second chart illustrates industrial load management. It compares two curves, a thick line representing the original, daytime heavy energy demand of a factory, and a thinner line showing what happens when that demand is shifted earlier. Utility companies use pricing incentives to convince massive industrial consumers to move their heavy power consumption into the late night and early morning off-peak hours. To further flatten that curve, large-scale energy storage devices are used as temporal buffers. They quietly soak up cheap, abundant power during the night and hold onto it, releasing it back into the system precisely when the evening rush hits. By changing exactly when electricity is consumed, grid operators maintain stability and prevent rolling blackouts without having to build massive, expensive new power plants just to handle a 2-hour evening spike. Inside a data center, the burden shifts to millions of erratic, instantaneous data packets. This diagram models a distributed computer network without load balancing. Because data requests arrive randomly, statistical fluctuations create a severe imbalance. You can see the heavily loaded nodes at the bottom visibly struggling with a backlog of tasks, while the lightly loaded nodes at the top sit completely idle. To fix this, data centers deploy a Layer 4 network load balancer. This piece of software acts like a hyper-fast traffic cop, rapidly directing incoming data based purely on IP addresses and port numbers. It doesn't care what's inside the packet, it just prioritizes raw speed to keep the network flowing. But sometimes, speed isn't enough. A Layer 7 application load balancer takes a slower, more deliberate approach. When a packet arrives, the load balancer actually opens it up at the digital gate, reads its interior contents like HTTP headers and cookies, and uses that specific information to switch the request into a specialized server lane best suited to handle it. Behind those lanes, dynamic algorithms like consistent hashing distribute the requests evenly across a massive pool of servers organized in a circular ring. If a single server goes offline for maintenance or crashes under pressure, the algorithm doesn't panic. It simply recalculates and gracefully remaps those specific data packets to the next available nodes on the ring. By parsing and reacting to chaotic variables in milliseconds, these systems maintain stability even as the server pool expands to handle massive, unpredictable traffic spikes. When you pull back and look at a functioning modern metropolis, with its flowing traffic, glowing lights, and streaming data, you are looking at the success of these invisible distribution systems in real time. The math of a steel truss, the scheduling of a factory, the logic of a hash ring, all converge on a single goal: preventing a localized failure from becoming a systemic collapse. The stability of these systems demonstrates that resilience isn't found in a single, unbreakable pillar, but in the efficiency of the network that shares the strain. But as these systems move from managing weight and data to managing our time, it raises a new question. What happens when the load being distributed is human attention?